So 2.5 similarity. Two polygons are similar now if and only if. I don't necessarily want you guys to underwrite it, but I want you to recognize that statement. This is what we call an if-then statement. If this is given, then this has to be true. Or if this wants to exist, then this has to be true. This language will be used constantly in mathematics. We're talking everywhere, all the way up to the top. It's like that's how our entire proof logic works in math. Okay? So just a fun little fact. There, and here's our 2 points. Number 1. Corresponding angles are congruent. Okay? And when we hear the word corresponding, right? We think back to our little warm-up up there where we had the 2 triangles, right? If I have a triangle let's say I've got a triangle. I'll redo the warm-up one from before. Okay. Let's say I have triangle A, B, and C, right? And then let's say I have another triangle in a totally different color. Dark green. There it is. Okay. It's even bigger. This triangle. Give me 3 other letters. I don't care. KJ? LKJ. Okay? Now, that's an L down there, sorry. And I say that this angle right here is 60. And I say that this side and this side and this side are all the same. Now, like we just said in the warm-up, that means these angles are congruent. For my triangle over here, I'm going to say that this angle is also 60. Yep, 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 and yep, and yep. Also 60. Right? So, that means that I can say for all of these angles, this works for all of them because they're all corresponding. And when we say corresponding, we're just talking about 2 angles that are in the same position and that are in the same angle measurement, right? Or not same position, but same orientation, meaning that as long as these 2 triangles, so if I turn LKJ sideways, those angles are still going to work to each other, so long as you just keep it consistent. So that means I can make the statements such as that angle LKJ is congruent to angle ABC. Or I can say that the angle KLJ is congruent to angle BAC. Everybody see how this is working out here as far as the first rule? All right. And that's the first rule. The second rule, so number 2, lengths corresponding sides are proportional. What it means by proportional is it's talking about essentially that the length of the sides are scaled up in the same proportion. Now, if you guys remember proportions, right, you should think, honestly, the first thing that should pop in your mind is what? Starts with an F. Food. Oh, okay. I see what you did there. Yes, right? And when you're baking, let's talk about baking. When you're baking and you say, what about a proportion? Well, you should automatically think of, well, what is it? Like, you need 2 cups of flour for every cup of water, something like that. I don't know. I don't bake. Sorry. So if anyone here is in baking club, I'm so sorry. I probably just botched that. Huh? Breaking. That actually is fair. Breaking Bad is also fair. Okay? Proportions are so important in mathematics because it's basically if I have a side that's 1 length, a side that's 2 length, and all the other sides follow the same proportion, then I'm good to go, right? So let's take another example of. So let's take a look now at some similar triangles that would display this. So when I'm talking about proportions, let's say I have. I'm trying to find a good one. Hold on. So let's take a look at this one. So this triangle, I'm going to show you guys right here. There it is. Okay. So let's say I have another triangle. Okay. This one I make slightly different. Okay, went a little off the rocker there on the right there. Sorry. But now, let's say I have these triangles, right? We've got A, B, and C, and I have D, E, and F, right? So, and of course, I'm going to state that, I'll use light green for this. This angle is congruent to this angle is congruent to this angle, and this angle is congruent to this angle. And I'm going to give you the sides. Darker, no. I don't know how to use pink. Use pink. 3, 4, 6, and 9, X, Y. Since all the angles are the same, then that means that, secondly, the lengths of the corresponding sides are proportional, which means that I have a hypothetical formula that states the following. That DE is over AB is equal to EF over BC, which is equal to DF over AC. Okay? Your algebra brain should be throwing a good hissy fit, I guess the best way to put it. I mean, they should be screaming at you right now. They should be like, wait a minute, I see something I could do here. Okay? You have a total of 2 variables defined with a total of 4 numbers. I like those odds. That means I can isolate one of them. All right? So, if I were to state such a fact, right, I could then state, well, DE is proportional to this guy right here. Okay? That means that EF proportional to BC. And I guess it's equal to. Like, keep in mind, do the order of these 3 fractions matter? Think back to your identity, your properties, back into the equation of the equal property, for lack of better words. It should not matter. They can go in any order because they're all equal to each other. Doesn't matter who goes first. So you can rearrange them, especially if you don't have the side that's in the next convenient spot. It's very good to know. But for this one, it is. So I can do then, let's see here. I can do 9 over 3 equals, EF was y over 6 equals, DF was x over AC, which is 4. I'm going to take the first two and solve for y. Okay, does everybody see where this is going? Good. Okay, 9 times 6 is? Oh, you said no? Yeah, sorry. So we're dealing with proportions, right? Since these triangles are similar because of their angles, that means that their sides, if they're proportional, which you would check for this, if they're proportional, then great. That means I can solve for missing sides in these triangles. The idea essentially is that, think back to dilations, all of these were scaled up by a factor of some number. That's what we cover dilations for. Okay? We scaled them up. Similar triangles are basically just scaled up one from another. They get bigger and bigger and bigger and bigger. Does that make sense? Okay? The factor of scaling, however, can be a little weird. Keep that in mind. But that's why we covered similarity. So it's a little callback back to, what was that, unit 1.6? No, 5. Yes. Sure thing. Sign up, leave your phone. Okay? So, let's take a look at this guy right here. Take him down. So we have 9 over 3 equals y over 6. How do we get rid of that variable? What do we do again? Anybody remember? Back. Huh? Why? How do we get him by himself, or how do we want to solve for him? We got to what? Yep, cross multiply. Very good. So from there, we get, what's 6 times 9? 54. Equals 3y. Divide 3 from both sides. What's 54 divided by 3? Should be 16, right? Put it away. Your phone. Come on, Corey. Should be taking notes anyway. All right. So it should be 16 equals y, right? Okay. We got 16y. So we put that number into there, and that means that it's proportional from there, and then we can solve for, here, right? We can put it here, and those two are proportional. We can solve for the other terms. So if we want to do the next one, I personally prefer to use the known values all the time and then the unknown value. I don't like to use the value that's been calculated, and you'll find that when we start dealing with things like decimal points in these down the road, it can get to become a nightmare. So I would say, to keep it simplistic, is to reuse 9 over 3 equals x over 4 and then just solve again. Cross multiply. We get 9 times 4 is? 9 times 4? 36. Yep. And 3 times x is? Oh, 3x. Duh. Divide by 3. 36 divided by 3 is? 12. So there you're missing sides. He's 12. He's 16. He's 9. All right. Does that make sense to everybody? The notes here, they just had you guys have the right to things out. I'm like, man, some examples would kind of help with this. All right. Now, the next thing we're going to talk about. I'm going to put an arrow next to this guy so I know where this starts. Okay? So what is this all leading to? It's leading to this. The fact that similar polygons have the same shape but are different sizes. Okay. Make sense so far? So let's say, voice crack? You can still get those. Pitch, voice pitched, either way. All right, let's say I have a small square. How long is that guy? About half an inch. All right. Okay. And I draw a bigger square. There we go. He's a little crooked on the bottom, but he gets the job done. Okay. These two shapes are similar. The symbol for similar, okay, which is just a squiggly line like this, without the equals, means is similar to. Okay? That is SIMILARTO. Like that. Okay? Which means that if we were to go back and look at that triangle, I could basically say that triangle ABC is similar to triangle DEF. Right? I check both rules off. Right? So, leave that there for a second before I have to flip over because I'm going to need more space for this next example. Because now we're going to go back and talk about those scale factors. Ah. Somebody double check 54 divided by 3. I thought it was 16, or I thought it was, now I'm doing my head. I think it was 18, wasn't it? So it's 3 goes into 5, 1. It's 18. I was looking at that because I'm like, that scale factor doesn't work. It is 18. Small little typo right there. So I'm glad I was looking. I'm just like, So it's 18. Therefore, then 6, 8. So then you'd have 4 goes to 12, 3. So the scale factor there is 3. Everything got multiplied by 3. 6 times 3 is 18. 3 times 3 is 9. 4 times 3 is 12. And now we're going to talk about that here in a second. I'm going to flip over and we're going to talk about scale factor. So this goes back again, all the way back to dilations. That's why we cover dilations, because some of the stuff overlaps. Okay, when we were dealing with dilations, when we dilated an object, right? Was it isometric after we dilated it? Was it isometric after we dilated it? Meaning, was it congruent? Or were they similar? They were similar, right? They got, as we scaled them up, they were the same shape, but they weren't the same dimensions. They got scaled up. Okay, similarity is all about scaling objects. Okay? So, here is the big example. The scale factor or similarity ratio right, is the ratio of the lengths of two corresponding sides of two polygons. I have to write the word two and not the letter two, number two there. Okay? Okay. Now, our example, just like our first one, I'm going to give you guys an example. This one's going to be a little easier. It's going to be a right triangle. And it's going to be even easier than that. It's going to be a 3, 4, 5 triangle, like one of the perfect ones, right? So, let's say I have triangle. There we go. Right? Right angle. A, B, and C. Call it a 3, 4, 5 triangle. Okay? That is a 5 there. I apologize. It looks like a demented 6. Okay? And let's say I have another triangle. Okay? Slightly bigger. Just a little bit. Okay? Again, these are not to scale. I'm just displaying a similar image here, so you might want to make a note of that. It's got a right angle, and it has the sides 6, 8, and 10. My labels for my points on this one are going to be E, D, and F. Okay? I'm going to make the statement that triangle ABC is similar to triangle DEF. Now let's prove that that's true. Okay? So, step 1. Okay? Is corresponding angles are what again? What are corresponding angles again? They are what? Congruent. So squiggly with two equal sign with the equal sign underneath. Okay? The measurement of angle C equals something the measurement of angle A equals something, measurement of angle E equals something, and then the measurement of angle D equals something. Okay? Now, spoiler alert, pretty much guess which all of those angles are going to be. If this is 9 degrees, right? And all the angles in a triangle always equal up to what? 180. And if I have 90, 180 minus 90 is 90. If I have two angles and those angles are going to be congruent, that means that the two angles, what's 90 divided by 2? 40 what? 45. So that means that this is 45, this is 45, this is 45, and this is 45. Everybody see how I did that? Now, if I really want to get fancy, there's a way we actually prove that angle using the sides, but we're not going to get into that today. We can use it just using basic congruence rules. Okay? So, all those angles are congruent to each other. Yay! My phone, sorry. Just ignore it. All right? Number 2. Shh. Come on, guys, look it up. Corresponding sides are proportional. Okay? Which means we can find some ratios. Yay. All right? We're going to look at AB over DE equals BC over EF equals AC over DF equals, okay? So let's put up some ratios here. Side AB was 3, DE was 6, BC was 4, EF was 8, AC was 5, and DF was 10. Okay? What do all of these reduce to? Yes. Should it? Leave your phone, take the horseshoe sign out. All right. What do all these reduce to? 1/2. Okay? Which means that our similarity ratio is 1/2. Which means the scale factor of this guy is what? Put that as a subpoint. What's our scale factor? What do we multiply everything by to move it up, to make it bigger? 2. Very good. Okay. And just because it's interesting, if we look at the perimeter of triangle ABC over the perimeter of triangle DEF right? So 3, 4, and 5. Let's see, 3, 4, 7, 5, 12, 6, 8, 6, 8. You should get perimeter of ABC gives me 12. Perimeter of this one's going to give me 24, which reduces down to what? 1/2. And you're done. Therefore, given that the corresponding angles are congruent, check. Given that the corresponding sides are proportional, check. The similarity ratio is 1/2, the scale factor is 2, check. And 4, that the perimeters are also 1/2, check. Therefore, in 3 dots in a triangular fashion, these two triangles are similar. So I will make the final statement down below. Therefore, 3 dots in a triangle fashion, triangle ABC is indeed similar to triangle DEF. Okay, so we're proving this. This is our result down here. And we're done. Any questions on that whatsoever? I'm going to pause the video here.